Hi. In the next lecture on Wednesday, we're going to talk about phase transitions, and we're going to talk about phase transitions from a macroscopic perspective, the way they've been analyzed historically in the 19th century. In the meanwhile, we understand them also at the molecular level, and it kind of helps to understand what's happening at the molecular level to understand what happens at the macroscopic level. So in this video, we're going to talk about the microscopic perspective, the molecular perspective of phase transitions. Before we do that, we need to talk about mechanics a little and about masses on springs. Remember, a spring is associated with a potential energy that depends on its elongation. If we have two masses on a spring, like these ones, there is a potential energy of the spring that is 1/2 of k times the distance between the masses minus d naught, the equilibrium distance. We can plot that as a function of distance, and the potential energy is this parabola, since we have a square dependence. So if the two masses are at rest, the potential energy is 0 here at the bottom of the parabola. If we now stretch the spring, the potential energy will increase. We're adding work by pulling the spring. We have to do work, and that work is going into the potential energy. So the potential energy is now higher, and we get to this point here. If we release the spring, what will happen is that the spring will pull on the masses, they will go inwards, and eventually they will compress the spring and be pushed outwards again. So they start oscillating like this. And note that the oscillations are between the initial stretch and some other point which has the same potential energy. So the total energy is actually conserved. So where does this potential energy go? Potential energy goes into kinetic energy. The masses now have velocity, and the total energy is conserved and stays at the same level as we had the initial potential energy that is on this black bar. So what's that to do with phase transitions in molecules? Well, molecules are very similar to masses on a spring, except that the spring between the two molecules, between the two masses of the molecules, is not simply following Hooke's law. Instead, it's got a potential energy that follows this red curve. The red curve will be dependent on which molecules and the orientation and whatnot. It's very variable, but roughly it always has the same features. It goes up very steeply when the molecules get close together. That's around here. And at large distances, it tends to some constant around here. And it doesn't go further up than that. And in between, there's this potential well, which is where the bond is, where the bond distance is. So if the total energy of the set of molecules is low, the molecules will be confined in this narrow range here. So if the total energy is, say, this k plus u is equal this value here, the distance between the molecules will kind of remain constant with slight oscillations around them. That is actually the case of solids. How is that solids? Well, now instead of taking two molecules, take a whole bunch of them. And what they are is that they all have to be at set distances, because that's where the minimum of the potential energy is. That's how far they can oscillate between each other. And so they just have this grid of molecules slightly oscillating around their equilibrium position. Now, if the energy is increased of the set of molecules, and the way that happens is through heating. We'll see soon enough that the temperature correlates with the agitation of molecules. The higher the temperature is, the more kinetic energy there is available. So if the molecules now have a higher energy, they will be able to oscillate wider. For example, if the total energy U plus K is around here, the molecule will oscillate between those two faraway positions. They're still bound together, but very weakly so. It's so weak that what can happen is that during one of those oscillations, you may have another molecule coming in from another oscillation, perturbing that whole thing. So you'll have something breaking this bond and moving along. So what that means is that molecules in this situation are quite mobile. They don't have to stay in place. They will just move along wherever they're pushed, but still staying together. And that is exactly what happens in the liquid. So this is the kind of energy level that is associated with the liquid state. If the molecule has even higher energy, if the black bar goes up here, well, the kinetic energy now exceeds the highest potential energy on the right. That means that it can keep on going and going and going, and the kinetic energy is not dropping to zero, so it can go on forever. That is exactly what happens in the gas. The molecules are no longer bound to each other. They can just separate freely and bounce wherever they may roam. Importantly, for a whole bunch of molecules, like in the gas or liquid, there's not just one velocity, there's not just one set of molecules. In fact, all molecules have slightly different velocities all around. The temperature will dictate the average velocity, but not each individual velocity. So on those energy diagrams, instead of having a single straight line like that, we'd have a blur of many different molecules at many different levels. And some of them might have a very high level. So even though you might be in the liquid state, here overall, there might be a molecule that is up here and that then can escape. So even a liquid at a liquid temperature can have a little bit of evaporation. Some molecules can leave it. So let's look at that in terms of molecular dynamics. Here we have a molecular dynamics simulation. It's from a software that you can get that actually runs on a web page, and the link is behind me. I'll put it on canvas as well. It's very fun to play with. So here we have 200 atoms in a box. And what I'm going to do is I'm going to increase the temperature, or what that means is I'm going to increase the average kinetic energy of the set of atoms. So every time I will click on faster up here, here the faster button, that means increasing the temperature. Slower would decrease the temperature. So we start off with a nice crystal lattice. All the atoms are right next to each other. And I'm going to press play, and there we go. We go faster and faster and faster. That means we're increasing the temperature. The vibrations are increasing in amplitude because the total energy is going higher and higher. So there's more room on the potential energy curve to vibrate. The atoms are also color-coded. When they go red, that means they have higher kinetic energy. They're hotter, each individual atom, if you like. So here we go. Now we have a temperature where there's quite a bit of agitation. In fact, we can start to see individual atoms actually vibrating. And if we increase the temperature even further, now you can see that some atoms are actually moving from one side to the next. If we increase the temperature even further, then a whole bunch of atoms are now moving. They're still sticking together, but they're still moving. What I'm going to do now is I'm going to, using this drag tool, I'm going to drag some atoms. And you'll see that by dragging some atom, the whole bunch of atoms follows, but it also deforms. And that's very much what a liquid is. It is a bunch of molecules sticking together, but you can make it flow. Now what you also see is that at this temperature, there's some individual atoms leaving this liquid. They are now free from the liquid. That means they are a gas. So here we have some molecules leaving the liquid progressively into the gas, and some molecules go back into the liquid as well. So we have this equilibrium between this liquid phase, between this liquid and the gas phase, the gas around it. Some of the liquid evaporates, some condenses, back and forth. Now, if we increase the temperature even further, the average kinetic energy of each atom is high enough for there to be no bonds left between the molecules, and that is exactly what a gas is. Now let's go back to the liquid. For example, it could be water. We've seen that water molecules leave the liquid water randomly. If there's no other water molecules in the air, eventually all the water would evaporate. But if there's some water in the atmosphere, some water molecules are randomly going back into the water. If the water concentration is high enough, the amount of molecules going back into the water will exactly compensate the water leaving, and there will be no net evaporation. We then have an equilibrium of water vapor and liquid water. The amount of water in the atmosphere is quantified by what is called its partial pressure, which basically is the fractional pressure due to the water alone rather than due to other molecules in the air. If 5% of molecules in the air are water, then the water partial pressure would be 5% of the atmospheric pressure. The partial pressure of water at which equilibrium between liquid and vapor is reached is called the saturation pressure. If the partial pressure of water in the air is less than the saturation pressure, liquid water will spontaneously evaporate even below the boiling point. If the partial pressure of water is higher than the saturation pressure, well, that actually doesn't really happen because then water starts condensing spontaneously In other words, it rains. That's why the relative humidity of air is given as a percentage of the saturation pressure of water. 100% humidity means it's raining, and the lower the humidity, the more water can evaporate. The saturation pressure is very much temperature dependent, and at 100 degrees Celsius, the saturation pressure is equal to the atmospheric pressure, meaning even if the atmosphere were entirely made of water molecules, water can keep evaporating. That is why it's the boiling point. Let's look at the detail of how a molecule can leave the liquid. In the liquid, most molecules have roughly the same kinetic energy. There's a spread, but none of them really has enough kinetic energy to leave the liquid. This is below the boiling point, so all the molecules want to stay together. But what can happen is that through a conjunction of events, several molecules can jointly give their energy to a single molecule that then have enough kinetic energy to leave the liquid. So let's have a look at the detail here in slow motion. I'll draw your attention to where the circle is, and there's a molecule here that, boom, it leaves the gas. So we're going to look at it in slow motion and in close-up to see what happens. Pay attention to the molecules around it that do collide with it. We're going to look at it again in very slow motion. I'm going to pause it here. Here we go. So look right next to the circled molecule, there's a red molecule. Red means it has higher kinetic energy than the average. And it bounces against our molecule, our circled molecule, giving it more kinetic energy, but that's still not quite enough to free it from the liquid. It still stays around, and then there's a second molecule giving it more kinetic energy, still not quite enough. And then the third colliding here, the yellow one, the third colliding, and finally it's getting enough kinetic energy to leave the liquid altogether. So here there were three, usually it's more like two molecules hitting a single molecule to eject it. And what's important is that this molecule that leaves, it takes away that energy from the other molecules. So that molecule takes away energy from the liquid. That means the liquid is losing energy. That means the liquid is cooling down. So when you want to turn, or whenever, in fact, whenever liquid turns into vapor, heat is removed from the liquid. If you want to maintain the temperature, that means you need to add heat. That is called the heat of evaporation, or the latent heat of evaporation. And we'll come back to that in more detail in the lecture. This was a very simple two-dimensional toy model, but there's actually was a research paper about 10 years ago showing that indeed for molecules to leave water, you need a conjunction of events. And what they showed is that you basically need two molecules that are already traveling together because they are weakly bound together. So that happens quite commonly, that a bunch of molecules will travel together, hitting the third one and giving it basically all the momentum through the collision to make the third molecule leaves. Schematically, we have two molecules traveling together, hitting a third one. Because they have double the mass of a single molecule, the velocity of the third molecule just becomes very large and enough to leave the liquid. So when molecules leave a liquid, they take away some heat with them. The converse is also true. If the gas molecules rejoin either liquid or solid, it does bring the kinetic energy with it. Remember, it's roaming freely in the gas, and then it hits the liquid and stops moving quite as fast. So it's got to give the energy somewhere. So it's bringing in energy. Here's another simulation with a single gas molecule that's going to hit a solid at the bottom, and you'll see it brings the kinetic energy and warms up all the solid. The solid goes from blue to red. So when a molecule leaves the liquid and becomes gas, it takes away heat with it. That means that to turn a liquid into a gas, we need to keep on bringing energy. And that energy is called the latent heat of evaporation. Same thing when you turn a solid into a liquid. To turn a solid into a liquid, to fuse it, to melt it, you need to bring in energy to break all those bonds. Conversely, when a molecule goes from gas to liquid, it brings some energy with it. And so if you turn a gas into a liquid, there is some energy released. It turns out that the energy required to evaporate the liquid is exactly the same energy that you get back if you condense the gas into the liquid. So it's completely reversible. You can turn some quantity of water into steam by using, say, 10 kilojoules. If you condense the steam back into water that will release the same 10 kilojoules again. You will not lose anything in the process. I hope that clarifies how solid, liquids and gases, the three main phases of matter, are different from each other at a molecular level and how one turns into the other. In each case, there's some energy involved called the latent heats, which we're going to discuss more in detail on Wednesday. Until then, cheerio.